All right, another video on L'Hopital's rule. This will be the third and final video on L'Hopital's rule. The idea was, I was hoping it would make the most sense to learn L'Hopital's rule by kind of getting this intuitive understanding of what's going on with L'Hopital's rule, kind of why it works a little bit, what the rule itself is. But to really use L'Hopital's rule, you have to be really good at understanding what an indeterminate form is. So I then spent a whole nother video just talking about indeterminate forms, coming up with all these different examples just to illustrate what indeterminate forms look like, but then not solving any of them with L'Hopital's rule, because I want to keep these videos as short as possible. So here's a third and final video where I'll go back to those examples and actually solve them. But there's a little asterisk there, because I'm not actually going to solve these 7 examples. This one turns out to blow up and get really, really ugly when you try to use L'Hopital's rule on it. So I'm going to change this one and solve a different problem. But otherwise, I'm going to solve all of these examples that I introduced in the previous video, going relatively quickly through them, just so you have a whole bunch of examples in your back pocket. So the first one, the limit as x approaches 0 from the positive side of the natural log of x over x to the negative 2 power. As we talked about in the previous video, this ends up being an indeterminate form, so we can use L'Hopital's rule. So I'm going to say that this equals and put a little h up on top of it to indicate to the reader that I'm using L'Hopital's rule. You don't have to do this, but if you want to keep track of what type of indeterminate form it is, which is allowing you to use L'Hopital's rule, you could write over out to the side somewhere what type of indeterminate form it is. This one's the infinity over infinity type, and that's because when x is a really, really small positive number, the natural log of x goes towards negative infinity, and x to the negative 2 power, if you put in a really, really small power of 0, also goes to infinity, positive infinity in this case. So you have this infinity over infinity type. So you use L'Hopital's rule by taking the derivative of the top and then the derivative of the bottom. So maybe you remember from a Calc 1 class that the derivative of the natural log of x is just 1 over x, which you can write as 1 over x or x to the negative 1 power, whichever is easier for you. I don't know, I guess I'll write x to the negative 1 power just so it'll look more like the derivative of this, x to the negative 2. Here I'm using the power rule, so I'm bringing the exponent down in front and writing this negative 2 as a coefficient, and then I'm subtracting 1 from the exponent to get negative 2x to the negative 3 power. Then the idea is for you to look at this and see if this is a limit that you can evaluate. And if it is a limit that you can evaluate, great, evaluate it. But if not, if it's still an indeterminate form, then you might have to use L'Hopital's rule again. And typically what ends up happening is to determine whether this is a limit that you can evaluate or not, you want to do some algebra. You want to simplify things here. So for example, if I multiply the top and the bottom of this fraction by x cubed, I would get x squared up top, and then just negative 2 down on the bottom. Right, x cubed and x cubed, this goes away, and x to the negative 1 times x to the 3 is x to the 2. Hopefully you can follow that. So really what this is asking me is what is the limit as x approaches 0 from the positive side of x squared divided by negative 2. And this is not an indeterminate form. This is a limit that I can evaluate. My values of x are getting really, really small, really close to 0. A number close to 0 squared is still 0, and 0 divided by negative 2 is still 0. This limit is just equal to 0 here. Next example. This is not one of the ones that I illustrated previously. Previously, I gave you this as an example of the 0 over 0 type. But I think this one might be a little bit more useful, a little bit more like what you'd see in a homework section or on a quiz or something. So maybe I solve this one instead. The limit as x approaches 0 of the sine of x minus x divided by x cubed. So I believe this is going to end up being the 0 over 0 type, so we'll be able to use L'Hopital's rule. But I guess before I do that, I should prove to you that this is the 0 over 0 type. The sine of 0, maybe you have that memorized off your unit circle from back in the trig days, is just 0. And 0 minus 0 would be 0, and 0 cubed would be 0. So this is kind of the 0 over 0 form. You don't have to write this. You can if you want. And then you can say that this thing is equal, using L'Hopital's rule, to the derivative of the top. So the derivative of sine of x is cosine of x. I guess I should leave my limit in there. And then the derivative of x is just 1. And the derivative of x cubed is 3x squared. And you're like, oh, okay, cool, now I'm done. I just evaluate this limit and call it a day. Well, in this specific example, I don't think this is a limit you can evaluate. Because if you change all the x's into zeros, the cosine of 0, if you evaluate the limit as x approaches 0 of cosine of x, you end up getting 1. Right? Think off your unit circle. The cosine of 0 is equal to 1. So 1 minus 1 gives me a 0 up in the numerator here, and 3 times 0 squared gives me 0 down in the denominator. In fact, after using L'Hopital's rule, I still have an indeterminate form. It's still the 0 over 0 indeterminate form. So I'm going to use L'Hopital's rule again. And this is still the limit as x approaches 0, but now it's the derivative of this thing. So the derivative of cosine of x is negative sine of x, and then the derivative of a constant is just 0, divided by the derivative of 3x squared using the power rule would be 6x. Now evaluate this limit. You're like, surely this is a limit that you can evaluate. No way you'd give me another indeterminate form and make me use L'Hopital's rule a third time. Well, actually, that's exactly what I did. All right, try plugging in zeros. Try evaluating this limit. The sine of 0 is just 0, so the top is negative 0, which is just 0. And the bottom is 6 times 0, which again is just 0. So I'm going to use L'Hopital's rule again because I still have this 0 over 0 indeterminate form. And figure out the limit as x approaches 0 of the derivative of negative sine of x would be negative cosine of x, and the derivative of 6x is just 6. And I think finally we've gotten to a limit that we can evaluate without using L'Hopital's rule. As x gets close to 0, the cosine of 0 gets close to 1, so I have negative 1 up in the numerator and 6 down in the denominator. This limit is equal to negative 1/6. The next thing I want to show you is what I refer to as the second type, so examples like this. Here are two problems of that type that I introduced in the previous video. So let's look at how to solve these. You look at this and you're like, no way, this is a L'Hopital's rule problem because everything I know about L'Hopital's rule, I have to have this fraction. Of course you have to have fractions. You can take the derivative of the top and the derivative of the bottom, right? That's what L'Hopital's rule does. No fraction here, no rational function if you want to use the proper terminology. So it can't possibly be L'Hopital's rule. Well, actually it is. And the reason it is because this is an indeterminate form. If you try changing all your x's into zeros, you'll get 0 squared, which is 0, and the natural log of 0 goes towards negative infinity. So I get a 0 times negative infinity. I have this type of indeterminate form, 0 times infinity. Similarly, I have this infinity minus infinity type over here. But the good news about these types, the 0 times infinity and the infinity minus infinity cases, is all you have to do is algebra to turn it into a fraction. What do I mean by this? Well, if you have something times something, multiplication and division are kind of analogs of each other. They're kind of similar operations in that you can always change multiplication into division. By just raising something to a negative exponent will often be the way to do it. So to change this multiplication into division, I really have two different choices. Here are the two different choices that I have, right? Either of these are algebraically equivalent to what I have right here. Either I can make the x squared x to the negative 2 and put it down in the denominator, or I can make the natural log of x raised up to the negative 1 power and put that down in the denominator. So either of these are perfectly legitimate, and I can try to use L'Hopital's rule on either one of these. However, as you start to get better at these, you'll know which of these forms will make your life easier. This one here will be hard. The reason it'll be hard is if you just look at the bottom and try to take the derivative, I'll have to use the chain rule. Right? First, I'll take the derivative of the negative 1 part here, bring that down in front, subtract 1 from this exponent. I'll still have a natural log of x left behind. And then I'll have to multiply that by the derivative of the natural log of x. The chain rule is going to cause the derivative of the denominator to be kind of ugly and to still involve natural log of x. So it's not ideal. This will work out really nicely because when I take the derivative of the bottom, I'll just have x raised up to some exponent. And when I take the derivative of natural log of x, that's 1 over x. In other words, x to the negative 1 power. What I'll end up with here is a really nice form. It'll be really easy to deal with. In fact, I've already done that. So the first thing I want to show you is this is the preferable form to choose of this guy as opposed to this. And then the second thing I want to show you is we've already solved that problem. All right, what I have written here is identical to what we have written here, so you can just solve it in that same fashion. Problem number 4 over here. This one's a little bit trickier. Generally, when you have an infinity minus an infinity, it's hard to change subtraction into division. It's easy to change multiplication into division, but subtraction into division is hard. And the reason you want division is because you want a fraction so you can use L'Hopital's rule. So how are you going to do that? Well, you have to create multiplication, generally speaking. If I could just create some multiplication, then I could change it into division like I did over here. And the way you create multiplication when you have multiple terms like this, infinity minus infinity, is factoring. So what you want to do is say that this is the limit as x approaches infinity of x times the natural log of x minus 1. Right, now I have something times something else, which is ideal because what I have here, I can change into division. Multiplication is easy to change into division, subtraction's not. The way I can change this into division, well, I got two options. I can make this x to the negative 1 power, or I can make this entire difference here to the negative 1 power. But maybe you can kind of see if you make this thing to the negative 1 power, the derivative will be hard to deal with. So it'll make your life easier to choose to make this the limit as x approaches infinity of the natural log of x minus 1 divided by x to the negative 1 power. Now that we've turned it into a fraction, we can check to see if L'Hopital's rule would apply. Often it does. Often when you have this infinity minus infinity, that will create a 0 over 0 or an infinity over infinity case. But I think in this specific case, it does not. All right, let's see how this works out. The limit as x approaches infinity of the natural log of x. This goes off towards infinity. And infinity minus 1 is still infinity. And then infinity to the negative 1 power. Negative 1 power, think about that as kind of 1 over infinity. 1 over an infinitely large number is going to get really, really close to 0. Right? Because the infinitely large number is positive, this is going to get really, really close to 0, but be slightly positive. So what's going on when I evaluate this limit is up in the numerator, I have something that is infinitely big and positive, and down in the denominator, I have something that is infinitely small and positive. So what's going on here is this is just going to get infinitely large, both because the numerator gets infinitely large and because the denominator gets infinitely small. So those aren't like opposing forces. They're both leading this thing in the same direction, both leading it to get infinitely large. And the final class that I want to show you, I introduced them in the last video as the green type, and those were the indeterminate forms when you kind of have exponents going on. So 0 to the 0, 1 to the infinity, or infinity to the 0 power, informally speaking. So I have an example of each of the three that I've copied down here, and what I want to do now is just show you how to solve them. So before I get to solving these, just one minor note. I changed this to the limit as x approaches 0 from the positive side, just so that later on the answer works out a little bit more nicely. So in case anyone was following really closely, I just wanted to call that out. So what you want to do when you're solving these third type of log problems, these log problems when you have an exponent making things weird, is you want to get rid of that exponent. And you're like, how are you going to get rid of that exponent? Well, there's a few different ways you can do it, but here's a little trick that I like that will be really useful for doing that. What you do is you name these things. So what I'm saying is I'm trying to figure out the limit as x approaches 0 from the positive side of x raised up to the natural log of x plus 1 power. Let's call that whole thing y. Call it whatever letter you want. I typically use the letter y. So y is the limit as x approaches 0 from the positive side of x raised up to the natural log of x plus 1 power. The thing you're trying to figure out, the question, give it a name, call it y. Why would you ever do that? Well, now I have an equation. When you have an equation, you can kind of mess with both sides of the equation. And messing with both sides of the equation will allow me to get this into a form so that I can deal with it. So specifically what I want to do is I want to take the natural log of both sides. If y is the same as all of this stuff, then the natural log of y is the same as the natural log of all of this stuff. And you can interchange the limit and the natural log thanks to the log rules that you learned in Calculus 1. What I'm saying is that this line is equivalent to this line. Right? Natural logs really help. Maybe you remember some log rules that you learned back in the day. There's these 3 different log rules that allow you to algebraically manipulate expressions that have logs in them. The log of a product, the log of something times something, is the sum of the 2 different logs. The log of a quotient is the difference in the 2 different logs. And the one that'll be really handy here is that anytime you're taking the log of something raised up to a power, you can take that exponent and bring it down in front of the log. Don't confuse that with the power rule, which says when you're taking the derivative of something with an exponent, you can bring that exponent down in front and subtract 1 from the exponent. That's a true statement, but that doesn't help us at all here. What we're trying to do here is use this third log rule, which has nothing to do with calculus at all. This is an algebra thing. It says when you're taking the log of something raised up to a power, you can bring that power down in front. And why is that so useful? Well, what makes these each so hard to evaluate are their exponents. Right? What makes these indeterminate forms tricky is they have these exponents. But if I can involve a log, if I put a log in here, then I can take that exponent and move it down in front. I won't have an exponent anymore, and it'll be a lot easier to deal with. But the problem is you can only do that if you have a log here. And if the original expression doesn't have a log down on the bottom here, you can't take the exponent and move it down in front, which is why I had to introduce a log. But you can't just go throwing logs in there unless you put one on both sides of the equation. So that's why I gave this thing a name, so that I can introduce logs to both sides of the equation, so that I can use this third log rule. This is a little bit hard to see, but this entire thing is the exponent here, the natural log of x plus 1. So I bring this entire thing out in front of this log. So here's that old exponent, natural log of x plus 1, and that's all in front of this natural log of x. What I've done is I've changed something that was an indeterminate form. It was the 0 to the 0 indeterminate form because this turns into 0 when I evaluate this limit, and the natural log of 1 is also 0. So this 0 to the 0 indeterminate form, I got it out of that form by involving logs. And that changed it from a power into a product. And maybe you remember from the red examples that products are good, right? I like having something times something. I like having something times something because I can always change multiplication into division if I need to. And then that division will look like a fraction. And if it's still in an indeterminate form, I can use L'Hopital's rule. So this ends up being kind of an iterative process. You get something that looks like green, you change it into something that looks like red. You get something that looks like it's red, you change it into something that looks like it's blue. And then the blue things are where you can actually apply L'Hopital's rule. And in each of those steps, make sure you actually have an indeterminate form, because if you don't have an indeterminate form, you can't use L'Hopital's rule. So in this one, for example, if I try to evaluate this thing, the natural log, the limit as x approaches 0 from the positive side of this thing. Well, let's see, if the x is really close to 0, this is really close to 1, and the natural log of 1 gets really, really close to 0. And then if I look at this thing right here, I got the natural log of 0, which goes off towards infinity. So this is the 0 times infinity, negative infinity technically case. And 0 times infinity, that's one of my indeterminate forms. So what I have to do is I got to change this into a fraction. Because each of these factors have a natural log, it doesn't matter too much which one I put on the top and which one I put on the bottom. So I arbitrarily chose to put this one down on the bottom by raising up to the negative 1 power. And now what I have is an indeterminate form. I have a 0 divided by 0 indeterminate form. Maybe you can convince yourself of that. So I can use L'Hopital's rule. The derivative of the natural log of x plus 1 is fairly easy. It's just 1 over x plus 1 times the derivative of x plus 1, which is just 1. And then down on the bottom here, it's a little bit uglier. The derivative of the natural log of x to the negative 1 power, well, I got to use the chain rule. So I take that negative 1 and bring it out in front, and then subtract 1 from that exponent to get negative 1 times the natural log of x raised up to the negative 2 power. But then I'm not done. I have to multiply that by the derivative of natural log of x, which is this 1 over x. And I get this ugly looking fraction inside of a fraction. But maybe you remember how to algebraically manipulate those. You certainly don't need to show all these steps, but maybe just for the sake of somebody whose algebra is a little bit rusty, let me show you what I'm doing. I like to, when I have fractions inside fractions, rewrite it so that it's a fraction divided by a fraction, and then I can flip the bottom one upside down to change division into multiplication. So in order to do that, first I got these negative exponents. This thing is just ugly looking. So I'm going to rewrite what I have here. Here's the 1 over x plus 1, and then this natural log of x raised up to the negative 2 power. I'm going to rewrite that as 1 divided by the natural log of x squared. So this negative 2 is this 2, and now it's a fraction down on the bottom here. Here's the negative 1. And then I still have my 1 over x. And by writing it in this form, it's easier to see how I really have a fraction divided by a fraction. I rewrote it just so you can see the x goes right here, left the top completely alone, and the bottom, instead of having it be a product of two fractions, is all just but one big fraction. And the advantage to having it in this form is I can take the denominator here and flip it upside down and put it up top. So here's the x natural log of x squared up on the top. And here's the x plus 1 down on the bottom. And the entire thing should be negative. And then you could stare at this and you could try to use L'Hopital's rule here. But my problem with this is if I try to use L'Hopital's rule, it would be a mess. Because not only will I have a chain rule here, but I also have a product rule. This x times all this stuff. Ooh, I don't like that at all. So what I'm going to do to avoid using a product rule is I'm going to multiply the top and the bottom of this fraction by 1 over x. That gets rid of this x, and then the 1 over x distributed into these two terms makes this a 1 and this a 1 over x. So that gets me to this line here. And I took it one step further just to make the derivatives easier to see. Instead of leaving this as 1 over x, I wrote it x to the negative 1 power, just so it'll be easier to apply the chain rule later. Anyways, I did all that work. None of that is calculus. That's just a whole bunch of algebra with kind of calculus in mind, getting it into a form that'll be easiest to take the derivative of, which is what I'm going to do now. But before I take the derivative, I should make sure that I still have an indeterminate form. So the natural log of 0 is negative infinity squared. That ends up giving me positive infinity. Down on the bottom, 1 plus this thing. Well, if I put a 0 in here, I have 1 divided by 0, which goes off towards positive infinity. I got an infinity over infinity case. I can use L'Hopital's rule. The derivative of the top, it's a little bit ugly. I got a chain rule. First got to take care of the 2 here. So I got 2 times the natural log of x raised up to the 1 power if you want. Then I'm still not done. I have to multiply that by the derivative of the natural log of x, which is this 1 over x. Taking the derivative of the bottom, the constant just goes away. The derivative of x to the negative 1 power is negative x to the negative 2 power. And this whole thing was negative, so that should be a negative there. Forgot the negative before, sorry. And now I look at this, I'm like, this is really ugly, but I bet I can clean it up algebraically a little bit. The negatives cancel each other out. This x to the negative 1 power and this x squared, I can multiply the top and the bottom by x to get here. The 2 still sticks around, the natural log of x sticks around, and then the 1 over x on the top, and one of these 1 over x's on the bottom, because it's squared, cancel each other out. So I'm left with x to the negative 1 down on the bottom, and I'm getting here. And you might think at this point, this is never going to end, but I have hope, because if you look at where we started using L'Hopital's rule, way up here, we had a natural log on the top and on the bottom. It was kind of a mess. We used L'Hopital's rule once and did some algebraic simplification, and the good news here is now we only have one natural log. The bad news is it's squared, so that's kind of annoying, but at least we've reduced it from 2 natural logs to just 1. And now if you take it a step further, we still have that one natural log, but it's no longer squared. So if I can do one more derivative, things will work out really nicely. Before I do one more derivative, I should make sure that I still have an indeterminate form. I do. The natural log of 0 from the positive side is negative infinity. 0 to the negative 1 power is positive infinity, since the 0 is coming from the positive side. So I have an infinity over infinity case. So I can use L'Hopital's rule one last time. The derivative up top, the 2 is a constant, sticks around. The derivative of natural log of x is 1 over x, or x to the negative 1 power if you want. And the derivative of x to the negative 1 is negative x to the negative 2. So that gets me here. And if you do enough of these, you start to realize that this is a great form here, because all I have are x's raised up to powers. So I can simplify this a lot. I can multiply the top and the bottom by maybe negative x squared. And what I would get is this is the limit as x approaches 0 from the positive side of 2x negative. All right, the negative, a positive divided by a negative is a negative. And then if I multiply the top and the bottom by x squared, these cancel out, and x squared times x to the negative 1 is just an x. And all that work, I finally got a limit that I can evaluate as the x gets really close to 0. Negative 2 times 0 gets really close to 0. Wow. It's about as hard as you can make a L'Hopital's rule problem, right? And you're like, oh, so I'm finally done. The answer is 0, right? I went through all this work. I got 0. I'm celebrating. I never want to look at this problem again. Nah, the answer is not 0. Why? Because what we solved for was the natural log of y. Ooh, what was y? Oh, right. Y is what I called the original question. Right? So what I've been solving for was the natural log of y. What I figured out with all this work is that the natural log of y is equal to 0. But the natural log of y is not my answer. Y is my answer. To get rid of this, I can do e to both sides of the equation and get y equals e to the 0 power. In other words, y equals 1. And since y is what I was calling this original question, right? That's what I called y. The answer to this question, this limit, is just equal to 1. Let's do a couple more, hopefully not quite as intense as that one. Maybe I can do it a little bit quicker. Same idea here. I want to call this thing y. The reason I want to do that is because I want to take the natural log of both sides of the equation so that I can apply my third log rule, which allows me to take this exponent and bring it down in front of the log. I think what you'll find is these first few steps are kind of the same on all of these types of problems, so many of you will probably jump from this step all the way down here in the future, rather than say that y is this, and therefore natural log of y is the natural log of this, and then use that log rule. You'll get to the point where you can jump straight from here to here. Like on this next one, for example, maybe I'll just say that the natural log of y, implying that y is this thing, is the limit as x approaches pi over 2 from the positive side of, I'm going to take the exponent down in front of the log that I'm about to create, I have the natural log of the tangent of x. So if you went straight from the first line to the fourth line, cut out the second and third line, your work would look more like this. And I think that that's fine if you want to go from here to here. If you're a little bit shaky in the algebra and you don't feel comfortable with that, show these steps until you're comfortable with them, and then this is fine going forward. Anyways, to solve these problems, well, let's look at this thing. Do we have an indeterminate form? Cotangent is cosine over sine. The cosine of 0 is 1. The sine of 0 is 0. 1 divided by 0 kind of goes off towards infinity. Ends up being a positive infinity, although it doesn't really matter at this point. And the cosine of 0, as I mentioned a second ago, is 1. And the natural log of 1 is 0. So what I have here is kind of an infinity times 0 case. And an infinity times 0 case is one of my indeterminate forms. It's a good indeterminate form. Multiplication isn't so bad because I can just change that into a fraction. When you have trig functions like this, because the reciprocals of trig functions are themselves trig functions, it's a little bit easier to change them into fractions. Because the reciprocal of cotangent is tangent, I can change cotangent into tangent by putting it down on the bottom of the fraction here. And now I have a nice fractional looking thing, a rational function. So I can apply L'Hopital's rule. Pretty good idea to double check, make sure that L'Hopital's rule really does apply here. The limit as x approaches 0 from the positive side. Cosine of 0, again, is 1. The natural log of 1 is 0. The tangent of 0, because tangent is sine over cosine, is also 0. This is the 0 over 0 type, which allows me to use L'Hopital's rule. The derivative of the natural log of cosine of x, well, I'm going to have to use the chain rule. I take care of the natural log part first. I got 1 over cosine of x. But then I'm not done. I have to multiply that by the derivative of cosine of x, which is negative sine of x. And then down on the bottom here, the derivative of tangent, maybe you remember this one, maybe you don't. It's secant squared x. So when I take the derivative of the top and the bottom, I get here, which is, as is often the case when I'm using L'Hopital's rule on these ugly looking things, is really ugly. But I think what you'll find is this simplifies pretty nicely. Let's see if we can do some algebra here to get this into a form that we can recognize. On the top here, I have sine over cosine, and it's negative. On the bottom, because secant is 1 over cosine, secant squared is 1 over cosine squared. So I can rewrite this entire mess as this. And the advantage of this form is now I have a fraction over a fraction. I can take the 1 upside down on the bottom and flip it upside down. And if I let this cosine of x cancel with one of these cosine of x's, I'm left with negative sine of x times cosine of x. And the good news is this is not an indeterminate form. So I don't use L'Hopital's rule again. You have to be careful. If you use L'Hopital's rule and it's not an indeterminate form, it's not like you'll get an error. You'll get the wrong answer. It'll provide an answer that's the incorrect limit. So you have to recognize this is not an indeterminate form because this is not 0 times infinity. This is 0 times 1. And 0 times 1 is just 0. This answer is just 0. So I'm done. No, careful. I mean, if I'm being honest, if this were a test and you left your answer as 0, I'd be pretty happy. I might even give you full credit, but you wouldn't get as much credit as your classmate who might get some extra credit by remembering that what you just solved for is the natural log of y, not y itself. Y is what we're calling the question. I have to say that the natural log of y equals 0, so therefore y is equal to 1. Y is e to the 0 power, which is 1, kind of like we saw over in this example. Last one. Given this mess, you recognize that you have these exponents. Oh, I don't even think I checked that this was an indeterminate form, although I did check it before using L'Hopital's rule. Cosine of 0 is 1, and cotangent of 0 is infinite. This is the 1 to the infinity, the second type of indeterminate form. But really, you didn't even need to know that because when we algebraically manipulated it, it changed into this 0 times infinity form, which we then changed into, I think it was the 0 over 0 form is what we changed it into before using L'Hopital's rule. So it's a good idea to always check that you have an indeterminate form, but it's really only mandatory that you check that you have an indeterminate form before applying L'Hopital's rule. That's the important step. Make sure you have an indeterminate form there. But since I'm teaching you this the first time, I'll go ahead and check that this is an indeterminate form. Tangent of x, because tangent is sine over cosine, and because the sine of pi over 2 is 1, and the cosine of pi over 2 is 0, the tangent of x acts like 1 over 0, which goes off to infinity, and then pi over 2 minus pi over 2 is 0, so I kind of have infinity to the 0 power. It's not super important, but it turns out that that infinity is negative, and that's because when I'm slightly bigger than pi over 2, I'm kind of over here in my graph. So I have a number that's really close to 1 divided by a number that's slightly less than 0. I don't know if you can even see anything from that picture anymore. The point is this is an indeterminate form. It's the infinity raised up to the 0 indeterminate form. So what I'm going to do is I'm going to transform it using log so that it's a product of two things. And when I do that, I bet I get a 0 times infinity case. Let's make sure that that's the case. If I try plugging in pi over 2 in all of these, I get 0 here, and here just a minute ago, we said that the tangent of pi over 2 is infinity, and the natural log of infinity is infinity, so I get 0 times infinity case. So just as I was expecting, this indeterminate form of the green type changed into an indeterminate form of the red type, which I'm going to now change into an indeterminate form of the blue type by writing this as a fraction. And you have options on what you do. Do you want to raise this to the negative 1 power or this to the negative 1 power? I think I want to raise this to the negative 1 power. So I put this x minus pi over 2 down on the bottom by raising it to the negative 1 power. And now I should have an indeterminate form. So I can use L'Hopital's rule. Let's make sure that that's the case. If I plug in pi over 2, I get the natural log of infinity, which is infinity. And then down here, pi over 2 minus pi over 2 is 0. And 0 to the negative 1 power is infinity. So this is the infinity over infinity case. I can use L'Hopital's rule. Now I take some derivatives. First, let's take the derivative of the top. Got a chain rule here. The derivative of the natural log of x is 1 over x. So the derivative of the natural log of tangent of x is 1 over tangent of x times the derivative of tangent of x. And the derivative of tangent of x, maybe you remember, is secant squared x. Down on the bottom here, I got to take this negative 1 and bring it out in front. And then I got x minus pi over 2 to the negative 2 power. And now I'm not quite done. I have to multiply by the derivative of this inside stuff. But conveniently here, the derivative of x minus pi over 2 is just 1, so you don't even have to write it. So, as is often the case, use L'Hopital's rule. You get a huge mess. But fortunately, algebra is your friend. You can use algebra to clean this up a little bit. The way I see this, x minus pi over 2 to the negative 2 power, I could make that x minus pi over 2 squared. And then I wouldn't have negative exponents to deal with. That's nice. 1 over tangent up on the top, I could just make that tangent down on the bottom. Secant squared up top, I could make that the reciprocal of secant squared. And since 1 over cosine is the same as secant, the reciprocal of secant is cosine. So I get cosine squared x down on the bottom here. The advantage to this form is tangent is sine over cosine. And so the cosine that's in the denominator of tangent here, if this is sine over cosine, and one of these cosines cancel each other out, and I'm left with sine of x, cosine of x. And let's see what I have. If I'm really, really lucky, this will be a limit that I can evaluate right now. If not, I might have to use L'Hopital's rule again. Well, the limit as x approaches pi over 2. The top's definitely going to be 0, right? Because pi over 2 minus pi over 2 is 0. 0 squared is 0. What about the bottom here? The sine of pi over 2 is not 0, but the cosine of pi over 2 is 0. 0 times 1 gives me 0. This is the 0 over 0 form. Because it's 0 over 0, I can use L'Hopital's rule again. Kind of interesting that it went from infinity over infinity form to 0 over 0 form. Maybe that's not that interesting. At any rate, I'm going to use L'Hopital's rule. Up on the top here, I kind of sort of use the chain rule, but not really. I take that 2 down in front. And then take the derivative of x minus pi over 2, but that's just 1. How convenient. Down on the bottom here, be careful. You got to use a product rule there. It's not that bad, right? The derivative of sine is cosine, and then leave cosine alone. But then you're not done. You have to add that to leave sine alone and take the derivative of cosine. So I'm going to add these two things together, but they're going to end up being negative. I leave the sine alone, and then the derivative of cosine is negative sine. There's where that sine came from. I get here. You can write that a little bit more neatly if you want. And then you stare at this thing and you're really hoping that this will be something you don't have to use L'Hopital's rule on. You're really hoping this is not an indeterminate form. I think you're in luck. The top is 0, right? If I change the x's into pi over 2's, I'm still going to get 0 up top, but the bottom's not. The cosine of pi over 2 is in fact 0, and 0 squared is 0, but the sine of pi over 2 is not 0, it's 1. And 1 squared is 1. So what I kind of get here is 0 divided by 0 minus 1. And so I get 0 over negative 1. This limit just evaluates to 0. That my answer? No, because we didn't solve for y. That's the natural log of y. So the natural log of y equals 0, so therefore y equals 1. It is not the case that these are always 1 is your answer. It's just coincidence that in these three it ended up being. So just something I wanted to point out. Wow, that was a lot of problems. That was a really long video. Sorry, I'll try to keep them shorter in the future. I guess the good news is now you have lots of examples you can look at if you want to look at them.